Hey everyone, welcome back to the Protocol Labs Research Seminar Series. Our speaker today is Dr. Nick Spooner. Nick is a postdoctoral researcher at Boston University and will begin a faculty position at the University of Warwick in January. He received his PhD from UC Berkeley, where he was advised by Alessandro Chiesa. His work focuses on post-quantum cryptographic proof systems, recursive proof composition, and zero knowledge. His talk today is on post-quantum succinct arguments. Nick, it's great to have you. I'll let you take it from here.
Thanks, Jonathan. Thanks everybody for coming. So I'm going to be talking about a recent paper, post-quantum succinct arguments, which is joint work with Alessandro Chiesa, Fermi Ma, and Mark Jandry. So I'm going to be assuming some amount of sort of crypto background and not really any quantum background. But if anything is unclear, then feel free to just shout out, stop me, and I'll be able to explain it. Okay, so let's start with what is a succinct argument. So a succinct argument is a proof system. So we may be familiar with zero knowledge proof systems. This is another kind of proof system where you have some NP relation. The typical NP relation is like there exists, or NP problem is there exists a witness such that XW is in this relation R, and you have a prover that wants to prove to a verifier that the XW that he holds is in this relation. We want sort of three properties from succinct arguments. The first two are properties you really want from any proof system. So if XW is in the relation, then if you run the honest prover, then the verifier should just accept. Soundness says that if X is not in the, if there is no W such that XW is in the relation, then the verifier is going to reject, even if the prover is malicious. So no matter what the prover does, if the verifier has an X that's which has no corresponding witness, then the verifier will reject with high probability. So far this hasn't really this is not very interesting, because the prover to do this could just write down the witness. And so we also add a succinctness requirement, which says that the amount of communication between the prover and the verifier should be bounded by, it should be polylogarithmic in the size of X and W, and potentially polynomial in some security parameter lambda that determines sort of how likely it is the verifier will accept a false statement. One thing that is important is that actually, in order for this to even exist, you need to relax this soundness property. Basically, soundness needs to hold only against efficient adversaries, and there's some complexity theoretic evidence that suggests that this is necessary. So you can't sort of have this strong soundness guarantee where soundness holds against all even computationally unbounded adversaries. So these constructions are going to be sort of cryptographic in nature, basically. And so classically, in the classical setting, we've known for a long time how to build these things. In fact, you can build them from relatively weak cryptographic assumptions. These are collision-resistant hash functions. And the natural question is, do post-quantum succinct arguments exist under standard assumptions? So in the classical setting, we can build them from really very standard assumptions. Does this carry over to the quantum setting? And in this work, we show that this is possible. So there exist post-quantum succinct arguments, assuming the quantum hardness of the learning with errors problem, which is the standard post-quantum assumption. And this is the first construction of post-quantum succinct arguments from any standard assumption, or even any falsifiable assumption. So there are some prior positive results in this work, in this line of work. but they make non-standard, non-falsifiable assumptions. So there is a similar result in the quantum random oracle model, which is an idealized model. So the quantum version of the ideal random oracle model, or you can also get them from these sort of lattice-based knowledge assumptions, but these are sort of non-falsifiable and kind of a bit shaky. Okay, so a natural question, which is sort of relates to what we were chatting about at the beginning of this talk, is we have collision-resistant hash functions that we believe are post-quantum, like built from lattices, and classically we can build succinct arguments from collision-resistant hash functions. So why not just swap them out, like take the existing construction, put in a post-quantum CRHF, and hopefully things will work out. Unfortunately, this is just not true. And the reason is that the proof of security, like in order to show that this protocol is secure, you need to do a thing called rewinding. And rewinding is something that is difficult in the quantum setting. It sort of goes against some of the postulates of quantum physics. And so one needs to be sort of very careful in doing the security reduction in order to make it work. What we show, though, is actually if you take this existing construction, this Killian succinct argument, and you replace the collision-resistant hash function with a slightly stronger function, which has a property called collapsing, then you actually do get a post-quantum secure succinct argument. And this collapsing hash function can be constructed from the quantum hardness of learning with errors. Okay, so this is sort of the setting. The next thing I'm going to do is I'm going to talk about Killian succinct argument, but I want to just stop and ask if there's any sort of broad questions about what's going on.
I have a question. I think I missed something. Is this interactive protocols or also non-interactive?
It is interactive, yeah. So,
okay.
Yes. So the non-interactive is a kind of a whole different setting, and non-interactively, we don't even know classically how to do this from standard assumptions.
Yeah, exactly.
Yeah.
Thanks.
Yeah. So, okay, but sort of interactively, we can hope to do it. We can do it classically for standard assumptions. We can hope to do it in the quantum setting too. Okay. So I'm just going to sort of recap this Killian's protocol from the 90s. It's quite simple. So you have a thing called a probabilistically checkable proof. This is a type of proof system where where the verifier, rather than like receiving the entire proof and reading it in full, it receives oracle access to a proof, which is potentially quite long. But it only needs to look at a few positions in the proof, sort of chosen at random, in order to make a decision. So this is the fact that these proofs exist was like a major breakthrough in complexity theory in the 90s. And using these proofs, you can actually build a succinct argument in the following way. So the prover is going to encode the witness as a PCP. So he's going to like build a PCP proof string for the statement that he wants to prove. This can be done efficiently. Then he's going to commit to the string in the following way. So the verifier is going to send the description of a hash function. And the prover is going to use that hash function to build what's called a Merkle tree. I don't know how familiar people are with these objects. So let me know if this is confusing, but basically it's a tree of hashes. So you sort of you hash together adjacent bits of the PCP, and then you have like a shorter string, and you hash together adjacent bits of that string, and you keep going until you get to the root. Then so the verifier receives his hash, and then he's going to choose. He's going to sort of play the role of the PCP verifier and choose a set of queries Q that he's interested in. So these are the positions that the PCP verifier wants to look at. And then the prover is going to open the Merkle tree to these positions. And a nice property of the Merkle tree is that the sort of amount of communication you need to open a position, like a leaf in the tree, like to decommit to a leaf in the tree, is logarithmic in the depth of the tree, right? Because basically you can open by revealing the sibling nodes of the path from the root to the leaf, and this is of logarithmic length. So it's like log of the size of the proof times the security parameter. Okay, so this is succinct, right? Because basically the number of queries. Okay, I guess one important thing to know is that the number of queries that you make to the PCP can also be very small, something like logarithmic in the size of the statement. And so if you sort of add everything up, you get some communication which is polylogarithmic in the size of the statement. Obviously the verifier is going to check all the openings, and then he's also going to check that the PCP verifier accepts on the values that are revealed. Okay, so this is succinct. The question is like, why is it sound? And the idea is we're going to appeal to the soundness of the PCP and use the fact that the prover had to commit to the entire PCP before he learned what these queries Q were. But in order to make that intuition into a formal proof, you have to sort of play this little game with the adversary. So the security reduction is going to go as follows. The idea is that we're going to take an adversary that is winning in the game, and we're going to be able to either extract a PCP that is winning with high probability, which is impossible by the soundness of the PCP, or we're going to break the hash function. So the way that you do this is that you run the adversary, you send him a choice of hash function, and he responds with a root, so some Merkle root. And then you're gonna play the verifier in the protocol. You're gonna send a Q, and he's gonna respond with the proof with some values pi q and some openings. So this gives you like a little bit of kind of what's in the prover's head, but not very much. And so in order to sort of invoke the soundness of the PCP, you need to really obtain from the prover like a full PCP string. And so the way that you do it is you just rewind the prover to the state S in the middle, and you run it again on a different queue. So always kind of randomly chosen. And you keep doing this over and over again. And eventually, if the prover is succeeding with high enough probability, you're going to fill in a good chunk of the PCP. And this is enough to break the soundness of the PCP. In particular, if everything is consistent, then you're going to find a good PCP. And if something is inconsistent, this means you find a hash collision. And so that's the proof of security in the classical setting. Are there any questions about this today? I'm not sure sort of how to pitch this. So was this too fast or too slow? Or
it's good.
Okay. Great. Okay. All right. So given that we're comfortable with this, I'm going to explain now like why this does not work in the quantum setting. So to do that, I'm going to sort of abstract the problem away a bit. So rather than talking about protocols, I'm going to talk about this abstract rewinding problem. So you have some algorithm A, and it takes as input an internal state S and a random string R, and it outputs some Z. Okay, so if we go back to this security proof, the state S is this S, right? So like the thing that's in the middle of the like the intermediate state in the middle of the protocol. The randomness R corresponds to the query set Q, and Z corresponds to the openings. So this is the sort of generic rewinding problem. And we know that the algorithm is convincing the verifier, so this is some verifier v, with probability epsilon over the choice of this randomness r. Right? So like I have some state s, and if I plug in r, then the adversary is going to output some z, such that this holds with probability epsilon, such that the verifier accepts with probability epsilon over the choice of r. And the idea is to is given that so suppose that we know that epsilon is quite large, so like much larger than k over the size of r, where this is the space of all randomnesses, so all the possible things that I could have sent here. We're going to try to obtain k transcripts RIZI, so this is like R and Z, such that the verifier accepts RIZI for all I, and all of the Ri are distinct. So we want to obtain sort of accepting transcripts for different choices of R. And this sort of corresponds to obtaining like correct openings for different query sets, which will allow us to rebuild the proof in the Killian setting. So classically, this is easy. It's sort of not even a problem that you would think about, because what you do is you just you take your algorithm A and your state S, and you just plug in random R over and over again until you find because the probability is large enough, you're going to find k different accepting transcripts after roughly k over epsilon trials. So this is the rewinding problem, and this is something that is sort of classically you kind of take this for granted. So just to sort of hammer this home, the classical adversary, like if you play the rewinding game, the classical adversary, the way that you like achieve this goal is just by running the adversary many times on different choices of R. And notice that all of these trials are independent, right? So like I choose this R uniformly at random, this S is fixed, and so all of these trials are independent of each other. And the probability that any one of them succeeds is epsilon, and so you can sort of do things with Chernoff bounds and things like that, and you can really understand how this process operates. Okay, so now quantum. What happens when A is a quantum algorithm? So now I've replaced the state S with the quantum state rho, and I have the same guarantee. So the adversary is winning in this game where he has to output an accepting response for a random R. And two things happen. Firstly, rho cannot be copied, and so this means that sort of you only have one copy of the state to kind of hold on to. You have to do everything. You have to do all of this rewinding using a single copy of the state rho. So in the previous, in the classical setting, we sort of made copies of the state S, and this was fine because it was just classical information. In the quantum setting, this is not possible because of the no cloning theorem. Secondly, so sort of in a relatedly, if you measure the state, so sort of hidden inside of this, there is a measurement of the state which produces this classical response set. So like the adversary is doing something that produces a classical answer, so this is going to be a measurement. And in general, the measurement that is applied to obtain this response Z is going to irreversibly disturb the state rho. So we sort of, once we apply this measurement to get Z, we cannot get the state back. It's going to be something else. So if we go back to our picture, what we have is now this this much messier situation where I have some randomness R that I plug in, and I have the state at the beginning, and I get an answer Z1. But then I can't just like take another copy of the state. So I need to keep the state that was left over after I made the measurement in order to try again. So the state is going to change sort of as I do this rewinding procedure. Okay, so Oh, is that a hand?
Yeah. Just I'm not an expert in quantum computing, but is it not possible to create to untangle many different pairs of states before the algorithm runs? So you have like already you prefix the number of copies you want to have at the beginning, and then something like this. I don't know.
Yeah. So the answer is no, because basically this state here, this row state, is already the result of a measurement. So because what you did was you in the first step you send this hash you send the hash function description, and then you get back the commitment, like the root of the Merkle tree. So there was already a measurement that happened here, which means that this state row is kind of randomized.
Nice.
And so if you kind of tried to do many copies in parallel, you would get different states row in each one, and they wouldn't have anything to do with each other. So yeah, so we really only have one copy of the state. Okay. So the question is, in this case, we had the success probability of the adversary in every case was in every iteration was epsilon, and everything was independent. Here, this is no longer true because the state has changed. But we can still ask, what is the probability that the adversary outputs a valid response in each of these steps in terms of the probability that he outputs a valid response sort of at the beginning. So notice that actually this trial here is going to output a valid response with probability epsilon, because it's just the same as playing the original game. But this is going to output a valid response with probability epsilon 2, say, and this might be different to epsilon 1. Okay. So in order to talk about this, I first have to introduce a notion which is very important in the quantum setting. It's called collapsing. And the way to understand collapsing is to think about two kind of quantum measurement games. So what is happening in this circuit? I have an adversary that takes in an input row. Takes in a state row as input and a classical string R, which is the randomness. This randomness R is going to be fed into the verifier circuit as well. But this A differs from the previous adversary that I was talking about in that it does not measure this output wire. So before we had this, you measured the output wire and you got a classical string Z. Here we've actually left it in superposition, so we don't apply a measurement here. So there is a quantum state on this wire, which is a superposition of possible output Z. And if you were to measure it, then you would get a Z according to this distribution. But we're not going to do that. Instead, what we will do is we will apply a measurement of a single bit. And this bit is, does the verifier accept the transcript RZ? So like, is RZ a valid transcript? This is going to collapse this wire to a superposition. So it's gonna produce an output B, which is either yes or no. And if you get yes, then this collapses the wire to a superposition of Zs which are valid. So where V of Rz is equal to 1. And if it's 0, then it's going to collapse it to a superposition of Zs which are invalid. Right? So it doesn't collapse it completely. It collapses it to one of these two things, either Zs that are all valid or Zs that are all invalid. But there is still sort of, in general, there's going to be a non-trivial superposition here. Okay. The thing that we do next is if this outcome B is 1, so if you get valid Zs on this wire, then we're going to measure this wire to obtain a single classical outcome Z. So this is now fully collapsed. If B is 0, then we don't apply this measurement and we leave the wire in superposition. So that's the experiment. So this is sort of an experiment where you only measure the value of the Z if you know that it's already valid. And how do you know that it's already valid? Well, you make a measurement to check whether it's valid or not. So this might seem, if you've not done quantum information before, this might seem a bit strange, but basically there are ways to sort of measure properties of a superposition without collapsing the entire superposition. And this is what is going on here. The second experiment, I take away this measurement. So now in the second experiment, I never make this measurement regardless of the value of B. Otherwise, it's the same. So I apply this V measurement and I obtain an outcome B. But then I don't do anything with it. I just throw it away. Okay. And now what I'm going to do is I'm going to think about the residual state, so sort of the state at the end of both of these experiments. And we say that a protocol is collapsing if its verifier V has the property that for every adversary A, which is quantum polynomial time, row 1, so the state after this experiment, is indistinguishable computationally from row 2, the state after this experiment. So note that these experiments are different, and so they sort of leave different states. But what we are going to do is we're going to require that no efficient adversary can tell the difference between this state and this state. So that's collapsing. And it turns out that Killian's protocol is collapsing, provided you choose the hash function to be collapsing. And what this will allow us to do is to say that this adversary A, rather than measuring this Z, we are going to sort of switch to this world, because this is an indistinguishable world. And we're just going to think about this single outcome B. So we can basically take this case where we really want to measure the Z, and now we're just going to measure a single bit, which is, does the verifier accept or not? This is important because basically the amount of disturbance that happens in this world is quite a lot, because you're measuring a large amount of information about the state. Here, you're only measuring a single bit of information about the state. And so this sort of intuitively means that you don't disturb the state that much. This is sort of at a high level, when you're making a quantum measurement, the more information you learn, the more destructive the measurement is. So we're kind of reducing the amount of information we learn to really just a single bit, which is the smallest non-trivial amount of information you can learn. All right, so let's return to this question about what we can say about these epsilon i's in terms of epsilon. And it turns out there are existing results on this. So now I've used collapsing to move A to be like a single bit measurement, and so these BIs are the same as, like, the probability that BI is equal to 1 is the same as the probability that A outputs a valid Z for the given R. And so in prior work, there's this bounded rewinding that says that if I run this K times, then the probability that I get 1 every time is at least epsilon to the 2K minus 1. So, this is something. This is a lower bound. Unfortunately, it is exponential in K, which means that while it's okay for constant K, although it does induce, it gives you sort of some ugly concrete security losses. But if you just care about polynomial security, then if K is a constant, then this is fine, right? Because this is going to be epsilon to some constant. But for succinct arguments, you want K to be much bigger than a constant. You want it to be like linear, really. And so this is going to be way too small. So one thing to note here actually is that this is quite a strong sort of statement, because it's saying that the first K trials all succeed. And the probability that this happens classically is actually epsilon to the K. Like, it's sort of not, it's also exponentially small. the way you get around this classically is you just like try a bunch of times. So you run a lot more than k trials, and if you run enough trials, then with high probability, you're going to see k successful ones across all of them, even if like any particular like fixed set of k of them succeeds with low probability. If I like look across all of them and I see, and I like count the number that are successful, I'm going to see at least k with very high probability. Unfortunately, in the quantum setting, this is just not true. So if you just do this, it turns out that these epsilon i's can still decay exponentially fast, even if you're even if you keep running for a long time. In fact, even if you run for an infinite amount of time, there are situations where the expected number of successes that you get is a constant. Like it could just be one success, even if you run for forever. So this is the situation. So this is sort of prior to this work where super constant rewinding was stuck. So the way that we're going to resolve this is we're going to modify the way that we do rewinding. So rather than just doing one trial after the other, and sort of accepting this loss on the success probability, we're going to design a procedure called the repair procedure, state repair procedure, which takes the state and it repairs the success probability. So the guarantee that we're going to get is that the probability, so if you apply the repair procedure with pretty good probability, this state is going to be as good in terms of how successful the adversary is as this state, this rho I state. And this means that we can now run a lot of trials because we're going to, like here we lose something in terms of success probability, we fix it again, and now this trial is going to succeed with good probability. And so we can just keep applying this step over and over again and get something that is essentially as good as classical. So one thing that's important here is that this rho I plus 1 star is not necessarily anything like rho I. So it's not like they're not necessarily like close in any way. And actually, if they were too close, then this would be impossible. So we're really sort of, we're allowing the state to be different to rho I. Like it doesn't sort of go back to the state rho I. But it is, we sort of restore the one thing that we care about, which is how successful is this next trial going to be. All right, so I guess I have 20 minutes or so. So I'm going to sort of give like an overview of the state repair procedure. So firstly, I'm gonna just briefly go through some like quantum notation. Apologies to people for whom this is familiar. So usually in quantum information, we use direct notation. So this ket here is a column vector, and this opposite of a ket is called a bra, which is the adjoint of this vector. So it's the conjugate transpose of this vector. And so you can write down the inner product of these two vectors like this. So you multiply a row vector by a column vector, where this is the adjoint, and then everything works out. So it's just a nice way to write the inner product of two vectors. So like I say, a quantum state is one of these kets. It's a vector in a complex vector space. And quantum measurement projects a state onto a chosen subspace of the vector space S. So this is the picture. So if I apply a measurement with the axes like S and so the orthogonal space to S, then if I get the outcome 1, this happens with probability equal to the squared norm of the projection of this vector onto the subspace, right? So this projection here is of size square root p, and so the probability that the probability that you get a 1 is going to be p. And afterwards, you're left with this with the same state but projected onto the subspace and normalized by this probability. So like you take this projection and then you just normalize it to make it a unit vector again. And if you get outcome 0, so you get outcome 0 with probability 1 minus p, right? If this is a binary measurement. And the resulting state is going to be the projection of the state onto this subspace, onto the orthogonal subspace, and then normalized. So one thing that's very important is that measurement disturbs the state, right? So when I make a measurement, the state moves to be to sort of match the outcome of that measurement. And secondly, it's generally irreversible in the sense that measurement is an operation that loses information, right? So if I project the state onto this S, all of the information about the S perp component is gone, is lost. So it would not be possible from like if I just knew the post measurement state, it would not be possible to reconstruct this state psi. This is sort of information theoretically impossible. Okay. I guess maybe just to say, like, measurement is the way that we learn information about quantum states. Like, you can't find anything out about a quantum state without making a measurement. So this is sort of the essential problem of quantum information. You want to find things out about states, but then doing so changes the state, and so you need to be very careful about what you try to learn about the state. Okay. So with that in mind, how do we do state repair? So I'm going to give like a very brief summary of the approach and then talk a little bit more about the specifics. So suppose that there is a space, like a subspace of the entire Hilbert space, so of the set of all states, like a linear space containing all good states psi. So this is having success probability at least epsilon. This is not true, but suppose for now that it is true. Okay, so the initial state is going to be inside of this subspace because the initial state, by assumption, has success probability at least epsilon. We apply a binary measurement. So this is our like algorithm A, which performs a binary measurement to get a bit B. And if you make a binary measurement, we're going to apply this principle where if you don't learn too much about the state, then the state is not disturbed by too much. In particular, the state is going to be somewhere else in the space, but it's not going to be too far away from this psi. And that means, in particular, if it's not too far from psi, then it's not too far from this S either, because psi is an S. Then what you do is you apply a quantum algorithm to rotate the state back into this subspace. And once you're back in the subspace, then because the subspace is like everything in subspace is good, then you can continue with the procedure. So you sort of repaired the state back to a good state. And this algorithm that we use to rotate back into the subspace is called alternating projections. So this is the basic outline, but there are a lot of sort of technical details that I've omitted. So the first one is that this first statement was actually not true. Sort of the set of all good states is just not a linear space. However, there is a linear space such that every state in the space is good. And if you have a state that is good, then its overlap with the space is pretty large. And so what this means is that you can take any good state, so like so you can take any good state, and this is like going to include the state at the beginning of the procedure. You can project it into this space S by applying the measurement, by applying this measurement pi S. And this is then going to succeed with reasonably high probability. And then your state is in this space S of good states, and then you can apply this this reasoning, right? So once you're in this space, then you can keep going back to this space. However, there is a sort of a much bigger problem, which is that we actually don't know how to implement this pi sub S procedure, this pi sub S measurement. So we don't know how to project onto the space S that we identified in the first bullet. However, there is an algorithm which approximately projects onto this space in a sense. So it's sort of close to being a projection, and the projection that it is close to is something that projects onto this space. And so what you need to do is basically do a bunch of analysis and show that if you modify this alternating projections algorithm a little bit, then you can also handle projections that are only approximately sort of projective. So that this is only like like what you really want is a projective measurement into the space. You don't have it. You have something that is somewhat like it, and you want to use it in place of a projective measurement in this alternating projections procedure. This is most of the technical work of the paper. Okay. So I guess I have about 10 minutes. So let me see. Okay, so I think maybe I'll explain just briefly how this, so this related problem of probability estimation, and then I'll give some indication as to how probability estimation actually allows you to do this approximate state repair thing. Okay, so probability estimation is the following problem. So you're given an algorithm such a quantum algorithm such that the probability over R that the algorithm outputs 1 is equal to P. And what you want to do is you want to estimate P using only a single copy of the input state. So note that if you have many copies of the input state, then you could just run the thing a bunch of times, like in the classical rewinding thing, and then you take the average, and this would give you a good estimate of P. But here we only allow you to have one copy of the state. So how do you do it? So there's an algorithm due to Marrott and Watrous, where what you do is you run this algorithm coherently. So here we had a wire going in that fed the algorithm a random R. What we do here is something called purification, where we take this random R and we turn it into a superposition, the uniform superposition of all R. And we plug this into the algorithm. So the algorithm is going to run coherently over all the possible choices of R. And so this bit B is going to be in the superposition of all of the executions of all of the algorithm over all possible choices of R. And then it will be measured to give a single bit. Then what you do is that you apply a measurement which checks whether this wire is in this state plus. So this is something that, that like classically we could do this part because this is really just applying A for a random R. This part is like really very quantum. So what you do is you're taking this wire and you're like saying, what is the overlap of this wire with the state plus after I apply this measurement? And if this thing outputs 1, then this wire is actually going to snap back into the state plus. And if it outputs 0, then it's going to be in some state that's orthogonal to plus. Okay, and so you do this. And then you just keep repeating this process over and over again. And the estimate is obtained as follows. So I define a bit di, which is equal to 1 if bi is equal to bi plus 1. So if the two adjacent bi's are the same, otherwise it's equal to 0. The estimate is the Hamming weight of the d1 up to dn. So you run this for just some n steps. The estimate is the number of ones in the string d1 up to dn divided by the length of the string, so the normalized Hamming weight of the string. And it turns out that d1 up to dn is distributed in some way. So it's distributed as a weighted sum of binomials, where the weights have this property that they, if you take the QJs, if you take a combination of the QJs with the PJs, then you get exactly the probability P you were interested in, which means in particular that this P tilde is an unbiased estimator of the probability P. So because if you take the expectation of this distribution by linearity, the expectation of this is n times Pj. So you end up with n times P, and then you divide it by n. So this is nice. I usually explain how this works, but I think I'm going to skip this. It's not super important to understand how it works. What I want to say is how you can use this. Like even if we don't know how it works, we can still use this procedure to actually get sort of the state repair in some way. So this is the theorem statement from the previous slide, except that now I've slightly sort of specialized it a bit. So before I had these QJs, and now I'm saying what these QJs are. They're equal to the norm of this number alpha j squared, where the state at the beginning of the procedure is written as sum over j alpha j psi j for some basis states psi j, which are eigenstates of some matrix. It's not that important. The important thing to take away from this slide is that so we can write this distribution of d1 up to dn in the following way. So we can, like, the following experiment has the same distribution as this d1 up to dn. And here actually I'm going to write d1 up to d2n. So I just I write 2n instead of n. So the distribution is as follows: you choose a j with probability size of alpha j squared. So these all sum up to 1. So this forms a distribution, and I choose a parameter p equal to p sub j, where I choose j with probability size of alpha j squared. Then I sample d1 up to d2n from a binomial distribution with parameters 2n and p. So these are like 2n independent coin flips, all of which have probability p of being 1. And this is the same distribution as this, except I replace n with 2n. So notice that if I analyze this distribution, if I sort of split this up into two parts, I think about the first n bits and the second n bits. No matter what p I choose in the first step, this sort of second step, I'm sampling independent, I'm sampling independent random bits, which are 1 with probability p, which means that I can use a Chernoff bound to show that this thing is going to be close to its mean, which is p times n, and this thing is also going to be close to its mean, which means that they're going to be close actually to each other. So the first n bits and the second n bits, if I take their Hamming weights, they're going to be within square root n of each other. They're going to be really close. So what this means, if you think about sort of how this could possibly happen, this must mean that the state in the middle is concentrated. So you remember that the probability that, so if I sort of cover up the first half of this procedure, it looks like running the whole procedure, but on this intermediate state. The probability that I get a particular outcome for this intermediate state is governed by this process where I choose some p with probability alpha j squared, and then I sample. But because I get some outcome which is equal to the outcome here with very high probability close to 1, it must mean that the alpha j squared weights have changed. So they were something at the beginning here, and now in the middle, they're different. And in particular, the alpha j's that correspond to the estimate that I got in the first half of the procedure have been amplified a lot. So they should be sort of close to 1. And all of the other alpha j's have been attenuated. So the amplitude of this state in the middle is concentrated on these basis vectors psi j that have good value, good eigenvalue. So how does this give you a repair procedure? Okay, so I'm going to run the estimation procedure on the state that comes out of this algorithm A. And if the estimation procedure outputs an estimate which is large enough, so which is close to this original P, then this means that the state is concentrated, like this state is concentrated on vectors, on basis vectors psi j, where the value, the eigenvalue, so okay, I should maybe hop back a sec. So the eigenvalue of these vectors is close to this P. What this means, so the eigenvalues of these vectors correspond to the probability that if I give you such a vector inside of this algorithm, that it outputs 1. And so this means that the output, because this state is concentrated around values that have around eigenvectors that have eigenvalue pj, this probability is also going to be concentrated around pj. Around p tilde. And this p tilde is roughly p. So sort of the end result of all of this argument is that actually, if I get an outcome p tilde here, then the state has been repaired. So the resulting state here, it's concentrated around this subspace of good states. And it turns out that actually, we've made this assumption at the top that you get a good estimate. It turns out that because of this gentle measurement property, the probability that this estimate comes out good is not too small. So, some of the time this is going to work. The problem is that the probability that it works, we need it to be really close to 1 in order to make this procedure work out. And so there is sort of a whole further step, which is you're going to try and force this procedure to output 1. And if you do it in a careful way, then this procedure to output something that is at least p tilde. And if you do it in a careful way, then actually this is not going to take too long to happen. And once it happens, then you can say that actually the state is repaired. That's sort of the 10-second summary of this final step. Okay, so that's all I have time for, and so thank you very much for listening. And if there are any questions, please let me know.
Thank you, Nick, and thanks everyone else for joining. Please remember, if you're watching the recording, to hit the like and subscribe buttons and share this video. Our next talk is next week on Thursday, May 20th at 1700 UTC from Sayoko Blodgett-Ford. She is a principal at GTC Law Group, PC and affiliates. Her practice focuses on intellectual property, data privacy, and security compliance. She also teaches artificial intelligence and the law, and mobile apps and big data legal contributions at Boston College Law School. There's more to her bio, but I can get into that more next week. If you're not on our mailing list, please sign up in the footer at research.protocol.ai. You can specify what types of emails you would like to receive. We send out monthly talk previews, quarterly newsletters, information on research funding opportunities, and more. If you have a speaker or topic suggestion for a future talk, please email us at research@protocol.ai. Thanks again, everyone, for joining, and we'll see you next time.